In this video, we're going to introduce something called Bézout's lemma. In the next video, we'll see how it's applied, but this is really just going to be devoted to establishing what it is. So here is the statement of Bézout's lemma. Suppose a and b are both integers and not both equal to 0. Let c be their greatest common factor. Then the set of multiples of c and the set of integer combinations of a and b are the same set. Specifically, on the left we have all integers times c, the greatest common divisor. So this is all possible multiples of the greatest common divisor of a and b. And here we have all numbers of the form ax plus by, where x and y are both integers. So this is all possible ways of taking a multiple of a plus a multiple of b. Multiples of the GCD are the same set as multiples of a plus multiples of b. So we can do a standard proof by showing these two sets are subsets of each other, and one of them we've actually already done. Specifically, suppose you have some sort of linear combination or integer combination of a and b. So z is an integer of the form ax plus by. Well, since c is the greatest common factor of a and b, it's definitely a common factor of a and b, and therefore a factor of a and a factor of b. And if c is a factor of both a and b, we've already shown it's a factor of all integer combinations of a and b. So c is definitely a factor of ax plus by, which means that any z we pick of the form ax plus by is a multiple of c, in other words, is something in this set here. So the set of integer combinations of a and b must be a subset of multiples of the GCD, and the proof in that direction of containment was really that straightforward. If a is divisible by c and b is divisible by c, then so is ax plus by, meaning any number of the form ax plus by is a multiple of c. So any number here belongs to this set. The real work is to show that the set on the left is a subset of the one on the right. That will finish the proof that the two are equal. Okay. So what we need to do is at least show that c itself is an integer combination of b. We want to show that all multiples of c are integer combinations of a and b, which means c itself had better be. Okay, so we'll do this as our first step. All we want to do is show that there are some integers x and y so that c can be expressed as ax plus by, that the greatest common factor of a and b is an integer combination of a and b. Once we show that, we'll finish the proof overall, that all multiples of c can also be written in that way. Okay, let's look at the set of linear combinations, all ax plus by. This set has some very useful properties. Specifically, if I take an element of L and another element of L, and I do the same thing to them where I multiply them by numbers and then add the result, I get new elements of L. Specifically, let alpha and beta be in the set L, x prime and y prime be integers, then I claim multiply alpha by x prime, multiply beta by y prime, add them up. That will simply be another element of L. Well, if alpha is one possible integer combination, ax1 plus by1, and beta is another one, ax2 plus by2, well then, alpha x prime plus beta y prime is a bunch of writing, but it can be expressed as, at the end, alpha times this whole mess plus beta times this whole mess, but this is just an integer and that's just an integer. So if both of these parenthetical terms are integers, we've said that alpha x prime plus beta y prime is a times one integer plus b times another, which exactly puts it in the set L. Okay? So anytime you start with two elements of L and take a linear combination of them, you get another linear combination of a and b. What does that have to do with what we're talking about, Bézout's lemma? Well, for two integers a and b, the remainder is a linear combination of a and b. And this just falls out from the division algorithm. If a can be written as bq plus the remainder, well then the remainder is a times 1 plus b times negative q. All you have to do is subtract bq from both sides and you get right here. So the remainder is a times one integer plus b times another. Okay, so remember our temporary goal is to show that the greatest common factor of a and b is a linear combination of a and b. We've just shown that the remainder is a linear combination of A and B, but we've also shown on the previous slide that any combination of linear combinations is another linear combination. Okay. Well, if one of A and B is 0, then the other can't be. That was part of our initial assumptions. So let's suppose temporarily that B is 0. Then the greatest common factor is A, and A can be expressed as A times 1 plus B times 0. So if B happens to be equal to 0, then the greatest common factor can definitely be expressed as a linear combination. What if the B isn't 0? Well, now the Euclidean algorithm comes in. So each of A and B is a linear combination of A and B. We've already seen that A can be written as A times 1 plus B times 0, but B can be written as A times 0 plus B times 1. In other words, A belongs to the set of AX plus BY, and B belongs to the set of AX plus BY. Any linear combination of things in that set also belongs to that set, and any remainder computations will be linear combinations and therefore belong to the set. So, since B and A are both linear combinations of A and B, in other words, they're both in the set L, the remainder is some sort of linear combination of these two. We expressed that on the previous slide, right up here, sorry. So since A and B are both in L, so is the remainder. So here I have two things in L, and therefore here are two things in L. Every time we execute the Euclidean algorithm, we start with two things in L, and then we replace them with a remainder computation. But the remainder was between two things in L. And we've already seen that if you have two things in L and you do a remainder computation, you just have a linear combination of those two things, which is therefore in L again. So you start off with B and A, both in L. The Euclidean algorithm says do a remainder computation, which is guaranteed to remain in L. So every time you do the Euclidean algorithm, both items in the parentheses can be expressed as linear combinations of A and B, but the Euclidean algorithm will always terminate with 0, comma something, where that is the greatest common divisor. Therefore, this thing here can be expressed as A times something plus B times something else. Okay, so how does that help us finish the proof of Bézout's lemma? Our goal was to show that the set of multiples of the greatest common factor was equal to the set of linear combinations of A and B. We already showed the set on the right, which we have been calling L, is a subset of the one on the left. We then showed that C itself is in L. Therefore, I can express C as equal to AX plus BY, but now we can complete the proof pretty quickly. If K is an arbitrary integer, in other words, K times C is an arbitrary element of the set on the left, well, C can be written as AX plus BY, and we simply distribute out that K and then refactor. And we have that K times C is A times one integer plus B times another. In other words, K times C belongs to the set L. So any element of the set on the left belongs to the set on the right. And that finishes the proof of mutual containment that these two sets are in fact equal. So we've completed that proof. Okay, multiples of the greatest common divisor and linear combinations of A and B are the same set. Any multiple of the GCD can be expressed as a linear combination of A and B, but conversely, any linear combination of A and B can be rewritten as a multiple of the GCD. And this is a fact we're going to make great use of in coming videos. The most frequent way we'll use it is what's already up here, that the greatest common divisor itself can be written as a linear combination of A and B. Any multiple of C also can, but the fact that C itself can be written as a linear combination, of A and B is the one we're going to use most frequently. Okay, so the next video will explore consequences of this identity and what we can use it for, but for now we've simply established it's true. Multiples of the GCD and linear combinations of the two integers form the same set.